For decades, the most important battle in computing was about making silicon chips smaller, faster, and more powerful. But now another race has begun. A race to build a machine that computes in an entirely different way. The quantum computer. Normal computers use bits, 0 or 1. Quantum computers use qubits, which can exploit properties like superposition and entanglement. And for certain problems, that completely changes what computation can look like. But here's where things get interesting. There isn't one quantum processor everyone agrees how to build. Different companies are betting on completely different technologies, trying to discover which architecture can eventually scale while keeping errors under control. Google's 105-qubit Willow processor demonstrated a major improvement in quantum error correction. And in 2025, Google used Willow to demonstrate what it called the first verifiable quantum advantage with its quantum echoes algorithm. It was the first quantum-at-break algorithm that could solve a problem no classic computer could ever verify. IBM is taking another approach, building quantum processors that work alongside classical supercomputers. Its Nighthawk processor contains 120 programmable qubits, while IBM's RootMap targets early demonstrations of quantum advantage and, later, fault-tolerable systems. And the competition goes far beyond Google and IBM. Quantinuum's Helios uses trapped ions. IonQ is developing its Tempo system. Microsoft is betting on a radically different idea, pavological POTAs, with Majorana 1. And D-Wave is scaling quantum attanding for specialized optimization problems. These numbers aren't directly comparable. These machines work differently. But the biggest enemy isn't another company. It's error. Qubits are incredibly fragile. Heat, electromagnetic noise, or tiny interactions with their environment can destroy the quantum information scientists are trying to preserve. A powerful fault-tolerable quantum computer would not simply make your laptop 1,000,000 times faster. Instead, it could attack specific problems that are extremely difficult for today's computers. Simulating molecules, designing new materials, studying chemistry, and potentially solving certain optimization and machine learning problems in completely new ways. And there is another consequence. A sufficiently powerful quantum computer could threaten public key encryption systems used across the digital world. That's why the transition to post-quantum cryptography has already begun, before such a machine exists. So the quantum race isn't about replacing every computer. It's about discovering who can build a quantum machine reliable enough to solve problems classical computers cannot. Google, IBM, Microsoft, Quantinuum, IonQ, and others are racing toward that moment. And whoever gets there first may help define the next era